with the Conservation Society. I'm hoping we don't have interruptions like we had last time. All I want to do then is introduce to you Michael Knight, who, the brief information I have, has a degree in history from Cambridge, which of course is the best qualification to get into IT that everyone knows about, better even than getting a computer science degree. Michael left Cambridge and went to work in the IT industry. He started with EMIDEC and then went down to ever after, at ICL. But he's going to tell us about Beacon. I think that's going to be very fascinating.
Okay, thank you, Mr. Chairman. Good afternoon, ladies and gentlemen. I was feeling, until minutes ago, entirely comfortable about this afternoon. Only it turns out we have amongst us a worrying number of Beacon veterans, which I never expected to see again. Never mind. It's particularly appropriate that this presentation occurs in these elegant surroundings of the Fellows Library, which of course is named after Phil Fellows, Univac's director of the Beacon Project. I'm really only going to talk about the first big stage of the whole Beacon project today, the reservations stage. Firstly, because of limited time, and secondly, because after that I was gone elsewhere and I don't really know anything about all the other applications, which I'll just towards the end briefly mention in passing. So the story actually starts in 1963, and to give it a bit of context, it would probably be helpful if those of you that can reset your internal clocks to 1963. We are, after all supposed to remember what we were doing and where we were when President Kennedy was assassinated. Or you might think of it as year 1 BB, before byte. The year before IBM unveiled System 360 and OS 360 and the 8-bit byte, which probably most people think dates from about the 5th or 6th day of creation. So, here in 1963, of course, terminology was different. We did not, for example, speak about IT, let alone CIT. We talked about computing or increasingly data processing. We didn't talk about operating systems, till IBM taught us. We tended to refer to things as control programs or executives. We had no use for the term database, since nearly all files, of course, were sequentially held on magnetic tape or, if not, punch cards. The concept was alien. And we didn't actually talk about transaction processing, or OLTP, as it came to be known. Instead, we talked about real-time systems, unless you were a die-hard member of BCS, in which case real-time had something to do with industrial process control. Another way, actually, you might get yourselves back into the frame of mind of 1963 is those beautiful lines from Philip Larkin's poem, Annus Mirabilis, which begins, "Sexual intercourse began in 1963, which was rather late for me, between the end of the Chatterley ban and the Beatles' first LP. So now we're there. Towards the end of 1963, British European Airways awarded a contract for a real-time system, initially to do reservations, and the winner was Univac. There really were only two serious contenders, not that that stopped some others, namely IBM and Univac, because those two had in production machines which were intended to support large numbers of terminals. And by the way, ultimately with the reservations system, we're talking about 450 terminals. And also they had in production and regular use large-scale, randomly accessible file storage devices. At that time, drums in the case of Univac and disks in the case of IBM. Also, those two could sort of claim they'd done it before, because there were 2 or 3 reservation systems. I'm not sure whether any were literally operational at that time, but if not, nearing completion in America. IBM had Panamac at Pan American, and also Sabre at American Airlines, and Univac had a system, I don't think I ever knew the name of that, at Eastern Airlines at Charlotte. Interestingly, neither IBM nor Univac at the time had what we would now call an operating system capable of seriously sustaining a large-scale online transaction processing system. As we'll see, they use something special for the purpose. Univac's proposal, I'm told by people who saw it, I never saw it, or the IBM one, was rather more voluminous and rather more detailed and ambitious and committing. In particular, it guaranteed a 2-second or better response time to about 95% of transactions, including at peak time, which is when it mattered most. And business for passenger reservations was very peaky. The period of maximum peak traffic was in fact in the middle of the morning for about an hour or so, Mondays to Fridays, which I remember bitterly well. We'll perhaps come on to that later. In addition, Univac offered what we would now learn to call a 24/7 service, which even subsequently with BOAC, IBM did not. And on top of that, they guaranteed, according to a carefully constructed formula, I must say, system availability 24/7 of 99.97%. This is 1963. So immediately we can see lurking there a number of design issues pending, which we'll get into. For the rest of the presentation, we have a structure. I'll talk briefly about what the Reservations Task was, for the benefit of such few people here who weren't intimately familiar with it. Then we'll have a quick look at the resources available to implement the task. Having done that, we'll look at some particular design features. And this needn't scare anybody with a rudimentary knowledge of computers in general, because there was no rocket science to it. Indeed, there was not really any computer science to it, which hadn't really been invented. And it was common sense stuff, really, coupled with a detailed understanding of what the hardware was and what it could do, and an understanding of what it actually was doing, which is the principle of operating systems, which seem to be observed in the breach long after this. And finally, a kind of requiem, a few words of, and what happened after that, Daddy? Spelling error there, but never mind. So, what about the task? The reservations function split naturally into 2 parts, really. First of all, there was what was called the inventory or numeric part. because it was just about counting bums on seats. Fairly fundamental for a business like an airline. And in fact, I'll talk for convenience about flights, but actually the unit of counting fundamentally was a flight class segment date. The flight number defined the route and the time of day, and indeed which days of the week the flight operated on. Class and date are fairly self-explanatory. What's a segment? Then, more than today, actually, flights often were multi-hop, or in airline parlance, multi-leg. And Beacon, I think, allowed for up to 8-leg flights. And I do remember one of them was London, Paris, Rome, Athens, Istanbul, Ankara, for example. Very tedious if you're going to Ankara, I imagine, but anyway. So the unit of counting was a segment. Now, what's a segment? A segment is a bookable one or more consecutive legs. So if you had a simple case like London, Paris, Rome, that potentially is 3 segments, yes? London, Rome, London, Paris, Paris, Rome, if the airline chose to make them all bookable. So that was the basis of the flight numeric files. And the first phase of the implementation was all about getting that done. To a large extent, Eastern Airlines had already achieved that with Univac. But they seem not to proceed rapidly on to the second part of the task, which is sometimes called alphanumeric or PNR, passenger name record phase. And a passenger record consists of one or more people travelling together on one or more flights. And incidentally, not all of those flights might be BEA. So a traveller would expect to be able to book on other airlines as well. And to that end, the numeric part of the operation had also something called availability, whereby other airlines would indicate to BEA, in this case, whether there was the opportunity to book on their flights, and which ones, etc., etc. And it might be various status, it might be book and report, it might be provisionally book and request, and so on. Now, so far I've concentrated on the fact there are a lot of online terminals involved, manned by telephone sales clerks, as they were known, and it really was perhaps Europe's earliest sizable example of a call centre system. Because that's essentially what it was. However, in addition, there was a lot of communication necessary with other airlines. And in fact, in those days, about 60% of BEA's bookings were made on it by other airlines. And to facilitate that, there was a pretty much global communications network dedicated for airlines' use. And run by not-for-profit and therefore customarily self-indulgent company called SITA, S-I-T-A. And we had a number of connections into the SITA network. It had a switching centre in London. Point to note here is that it was a telegraphic network. At that stage, 75 bits per second typically, simplex lines in and out, and an awful lot of traffic. And there was a protocol for the messages, covering all the sort of predictable airline uses, which was called AirImp. Again, an important thing to remember is that practically in those days, practically all those messages, of course, are originated at a teleprinter by hand, and as such, subject to error. which didn't matter very much if you've got an experienced person on the other end receiving the message and unscrambling it. Did cause problems for early computer systems though, but not Beacon, as we will see. So that essentially, in a nutshell anyway, is what the task was about. And potentially there were thousands of transactions a second. One call, for example, would yield several transactions, one for each flight required. That'd be a message pair. One for each different name in the party. Then there'd be contact details, accounting details, special needs, like vegetarian meals, wheelchair help, travelling with double base, etc. So that was a task. If we now start to look at what are the resources available for the purpose, we could start with the hardware. At the heart of it all were two Univac 490 mainframe computers. Not that I think we call them mainframes then either. One was online at any one time and the other offline for development and diagnostic purposes or nothing much in particular. That was the approach. Each machine had 32K 30-bit words, which could be addressed incidentally as whole words, half words, third words, or fifth words. The fifth word being, of course, six bits, which would accommodate an old-fashioned character. Not a particularly fast machine, even for those days, but that doesn't really matter. It didn't matter, because in general, we can say that transaction processing is not compute intensive. What there is, apart from a certain amount of data manipulation, is what used to be called early primary school level arithmetic. Adding up and taking away and times and into. So no rocket science there either. What was crucial to performance and system capacity, however, was file accessing, which I guess is probably as true today as then. Univac, as I said, still for some time in the future relied on drum technology for file storage. I'll show you a couple of pictures of these in a moment, not that they're exciting visually. There you've got the basic details of the capacity of the respective units. FH, depending on your taste, incidentally, stood either for fixed head, because there was a read-write head per track on the drum, or flying head, because in fact they weren't in contact with the drum surface, but flew aerodynamically on a thin skin of air dragged around by the 1800 revolutions a minute of the drum. Point to note is that the fast RANs did have moving heads. And you can see not a terribly exciting average access time, except that in the case of Beacon, actual access times are about 2/3 of that. The scanner selectors were used to support local buffer processors, which I'll explain in a moment. In addition, there were multiplexers, which eventually would be used to support remote buffer processors and groups of terminals in about 10 different sites in UK and Europe, and also to support the lines in and out of that CETA network. 1004, some of you will probably remember, was perhaps the ultimate in plug-board program computers. But it also came in very useful as an economical low-speed input-output subsystem with a card reader, optionally a card punch, and a 600 line a minute barrel printer, which made in a confined space an appalling, shattering amount of noise. The magnetic tape drives fundamentally were there to back up the drum files. And if memory serves, about every hour the flight files on the smaller drums were backed up, and about every day, in due course, the passenger records and indices were backed up. The buffer processors were, I think, quite interesting because really they were terminal cluster controllers. They had 8K of 7-bit words, took 2 words for a program instruction. And their function, as the name suggests really, was literally to buffer from the, inputs from the agent sets, which we'll come on to, and forward them through the scanner selectors into the online system. And then the agent sets. Well, let's look at 1 or 2 pictures here. That's an FH880. I should think from memory, maybe about 4 feet long and 3 feet diameter drum. Ponderous thing. And there, I suppose they stood about 6 feet high or so, fast ran units. And if you tot it up all together, the amount of random access file storage which Beacon had by the end of the reservation service, it amounted, although of course most of it was duplicated, it amounted to a staggering nearly 3/4 of a gigabyte, or about that much. It's getting difficult to find a laptop now with less than 2 gigabytes of main memory, isn't it? And there's a picture of an agent set. From the point of view of the buffer processors and the system generally, I mean, it looked like a teleprinter, and indeed it partly was a teleprinter, which is largely used when we got to the alphanumeric stage of things, passenger records. Otherwise, it consisted of a number of buttons and lights which guided the telephone sales clerk through the requisite functions and made sure that none were left out, Here you can see a slide. When having determined which flight or which route was required for a journey, the operator would get out of a well at the side of the terminal one of these slides applicable to that route, and then select a flight within it from buttons along the side. Coding on that slide would automatically tell the system which route you were looking at. VDUs, video display terminals, were rare indeed at this time. And indeed, we didn't call them VDUs anyway, they were CRTs, cathode ray tubes. The early reservation systems, whether IBM's or Univacs, used something similar to this. Now, you're not meant to take notes about that, but that shows you the configuration diagram which happened to turn up in the attic. It actually dates from the end of 1967, and it just gives you the flavour of the thoroughly duplicated hardware complement of the system. if you've got keen eyes, what you may notice on there is that the two computers suddenly are 494s. This was because at that stage the 490s were replaced by the successor product 494s in anticipation of all those subsequent applications being added in. And the great beauty about 494, it was about 6 times faster, but that was immaterial really. More importantly, you could actually have 64K words of memory on it. Astonishing. One thing before we get on to software, that memory on the 490s didn't have memory protection on it, unlike the totally dissimilar Univac stablemate, the 1107, where you could actually lock in an area of memory in multiples of 2K words, which would prevent other programs running concurrently invading that space. We didn't have that on the 490, and we were very pleased because we could not afford granularity as large and profligate as 2K words. We needed every bit, every binary digit that was available in there. On the other hand, we did have a period which certainly many weeks, I can't recall mercifully how few months, where we suffered grievously from the lack of memory protection after we cut over the second phase, incidentally. Because every morning peak time, a bug, which with hindsight we should have spotted far sooner, but anyway, a bug added 1 randomly to a memory location, anywhere. And so every occasion was unique, of course, in its dire consequences, and was elusive because the combination of circumstances which had triggered that bug were long gone by the time the system crashed. Right, software. The 490 came with an operating system called REX, Real-Time Executive, which was not very much use at all for any serious real-time system purpose. And so we only used REX offline in order to run the assembler program, which Univac provided, which for some reason was called SPURT. Instead, on the online system, we had our own operating system with what I always thought was an extremely inelegant name, Contorts, Control of Real-Time Systems. And Contorts was developed as necessary and elaborated as necessary with progressive implementations of the applications. Now, REX and SPURT, the assembler, were the only standard issue Univac software we used on Beacon. And the story was not dissimilar, incidentally, on the early IBM systems, where they had something, not a standard operating system, but something called ACP, or Airline Control Program, which I would describe at my peril as a pale replica of Contorts, really. Very specifically geared for serious real-time, but Contorts was much more interested in resilience. It was a 24/7 service, it had to be, and also reflected the duplicated nature of the hardware configuration. One of the things which Contorts also supported was something we called re-entrant programming. in which programs were not allowed to modify themselves. That may be a self-evident truism nowadays, but it wasn't then. Basically, all transaction processing was done in relation to an area called transaction data, a sort of scratch pad for the life of the transaction in the system, addressed via an index register. So it was possible, in effect, to multi-program several transactions through the system concurrently without anything colliding. Similarly, Contour supervised services like record locks, because if you're going to have several different programs or instances of a program accessing the same files, then you do not want collisions and double updatings and so on. So a process of record locking, if you're expecting to update the record, was available. You'll have gathered that all this programming was very much low-level stuff using the assembler. So one line of code, written on a pad, by the way, obviously, not on a keyboard and screen, represented one instruction, one word of memory. And we kept very tight control of that, actually. Typically, if you're about to write part of the application, you would get a sort of provisional budget of how much memory you were allowed to use, how many drum accesses, and so on. And you had to argue very cogently if it turned out that really wasn't quite enough. We did toy with a high-level language at one stage, actually, which you won't have heard of, outside Beacon, called EMIDEC. So called because it was developed by the Navy Electronics Lab in San Diego. You could think of it as Algol Light. It was an algorithmic language. What was interesting from our point of view was that it was self-compiling, so it was written in itself and therefore very amenable to being extended as necessary. But in practice, so far as I'm aware, it never really got used to any degree on the actual reservations task. I could say a word here in passing about documentation and training on the project. Neither of these things were amongst the glories of the Beacon system, I have to say. In fact, sometimes there wasn't any training at all, and there wasn't very much documentation either. You've got to remember, actually, that this is a era before, photocopiers on every corner. So if you needed more than 2 or 3 carbon copies off the typewriter of something, then you'd have recourse to Gestetner or Roneo or whatever. And the trouble was that, for example, in the case of contorts, there was a manual for contorts, usually out of date, because it had moved on. And in any case, not in plentiful supply, because it wasn't worth actually printing them. And of course, it was a darn nuisance to replicate without photocopying. Training was pretty sketchy as well. And experienced programmers, of course, didn't need really a course. You give them the processor manual, you give them the assembler manual, off you go. However, it would have been helpful if we'd done more sooner to educate newcomers onto the project about what the project was about and what its component elements were. I worked on a particular part of the system, and I had very little idea until that was all done what all the other things did. There were mysterious things like, for example, a suite of programs called schedule change and nightly update. How often I wonder what they did. But anyway, they were an instance of programs running in the background alongside the online operation. When you think about it, with a 24/7 type system, everything's got to be alongside, including things like, when necessary, file recovery. So if, for example, you lost some drum unit or controller or whatever, the contorts would automatically degrade to make use of what was left. By and by, when you got your unit back, you'd need to reconstitute your second copy of the files. So you do that concurrently with ongoing operations. But when you think about it, that isn't a terribly easy trick. Not something you program in an odd afternoon, because the files are still randomly updating while you're copying. So contorts in all those sort of respects was a pretty clever beast. The next dimension is time. The reason that the reservations project itself was divided into 3 successive phases was partly to expedite return on investment. Because for those days this was a seriously expensive system. The hardware bill alone was in the order of £3 million, which is perhaps 40 to 50 million today. So there's a need to show some return on the investment as soon as possible. And in fact, the first phase, the numeric inventory phase, was cut over in Easter 1965, apparently 16 minutes ahead of time. Presumably people wanted to get to the wet lunch afterwards. Unfortunately I wasn't there, missed it. The second phase was supposed to cut over in Easter 66, and it didn't. Why this emphasis on bank holidays? Well, the interesting thing about bank holidays is they're long, and although they're a very busy operational time for an airline, they're a very slack time as far as new reservations and other such business is concerned. Therefore, you have an opportunity, in effect, exceptionally, to take the system off the air while you put on the next phase. And when you think about it, just logistically, never mind technically, it's a difficult trick adding subsequent phases after the first one on a round-the-clock system. And you think about the logistics, BEA, most people who can remember BEA might not realise this, was at that time the 5th largest passenger airline carrier in the world, carrying about 7 to 7.5 million passengers a year. No big deal nowadays, but it was a lot then. And the records stayed on the system for a period of 11 months ahead of the actual flight date. So a lot of records. If we take passenger records, for example, bearing in mind that more than one passenger could be on a record if they're on the same journey, there are perhaps something like 2 million passenger records. Now when you come to cut those over onto the system, the first problem is, how do you transfer those couple of million handwritten cards onto the system? And the answer was, well, you pay a lot of overtime to large numbers of sales clerks to work through the bank holiday, keying them in, which also gets them more, very familiar with the new phase of the system and how that's used. However, to begin with, you've got to train them. And if you've got perhaps 300 or 400, how are you going to get phase that? Such that the first people to go on the course haven't totally forgotten about it by the time the last people have done it. So a big logistical problem anyway. And on top of that, well, the way we tackled that was by geographic area. If memory serves, Benelux was the first geographic area to go on that second phase. But Easter 1966 came, and to put it briefly, we failed to get the second phase cut over successfully, and had to revert, therefore, to previous mode of operation for the Tuesday morning. And in fact, the core members of the project team didn't get a bank holiday off that year until Christmas, because that's how many goes it took to actually finally get the thing successfully cut over. And then some problems started. Okay, people is my last category of resource. The project comprised about 25 to 30 programmers, roughly equally divided between airline staff and Univac staff. Until the reservations project was done, system responsibility remained with Univac. And there were incidentally penalties attaching to those guarantees of performance and availability, largely in the form of withheld maintenance charges, which ordinarily would be quite considerable, because there was also about 10 site engineers to provide round-the-clock engineering cover to deal with hardware errors. Not 10 at a time, but in shifts. The project was organised in teams, about half a dozen teams, ranging in size from perhaps 3 to no more than 6 people in each team. And this was we tended to feel was a very optimum type of project size, something which might be ruminated about by some government departments this very day. Because it meant that whoever was in overall charge of the implementation dealt in the first instance with about half a dozen people, team leaders, who incidentally were selected on perceived merit and contribution to the work, and again were pretty much evenly divided between BEA and Univac staff. And then each team leader had no excuse for not being pretty intimately aware of what each of his guys was doing. I say guys, we did have a sizable minority, I couldn't give you a numerical breakdown, of women programmers as well as gents. One thing I haven't mentioned, you may have noticed, talking about people, is analysts. During the reservations implementation, it changed subsequently, I must say. We didn't have analysts as such, because the feeling was we were so critical on optimum exploitation of the hardware that you really didn't want some other breed of creature mediating trade-offs between performance and, or availability for that matter, and nice to have features and so on. So, I mean, where necessary, programmers would deal directly with end user representatives. And in fact, somebody who should be nameless once described to people on a training course what we considered analysts to be on the Beacon project, the opposite of catalyst, namely an agent which, well, having no active part in the process, nevertheless impedes its progress. Sadly, amongst the audience on that occasion were some BA analysts and the manager of systems analysis who gave assurance that that would change in due course, which it did. Oh, well, save that for later. Design issues now. My first design topic was, if you remember from that summary, design for failure. Now you can see from the configuration that we had hardware failures, along with the round-the-clock engineering cover, pretty much sorted. And the engineers were inclined to say, well, someday, guys, you programmers, you'll actually get your software right, and after that you'll be home free because it won't go wrong. Whereas hardware is always going to go wrong from time to time. And we weren't so sanguine, actually. We were quite sure the software was going to go wrong, and the system was basically designed around the assumption that it would. And we were not disappointed in the event. So the key to maintaining that high level of service availability was rapid restart. And if you think about how long it takes you to bootstrap your Windows Vista or whatever currently, you may be interested to know that a manual restart where everything would be switched over through those transfer switches by a button, or as much as you wanted to switch over anyway. The two host systems would be switched over. They start up, the now online system would do something, well, both systems in fact would do something called, which we called in the parlance of those days, grope. In other words, they would feel about to see what they had. Were they the online system or the offline system, and how much have I got of that? Have I got one of those, etc., etc. Then it would pick up interrupted transaction processes where they left off. In other words, as I said before, let's say somebody calls up, wants to make a booking. That's going to give rise to a number of transactions. Inevitably, it might be 10 or more. Rather than have to go back on restart to the start of the whole booking process for that customer, you go back to the last completed transaction, the last message pair. Because there will be a log maintained on the drums of the status of every dialogue, if you will. Now that whole process of switching over, restarting, rebooting, picking up where you left off with all the active terminals took 30 seconds. Part of Contorts was something we called SICOM, which was system commands. And that too evolved as the system evolved. And basically this was a set of operator commands where you could manipulate, as desired, the configuration and its activity. So in times of pain and stress, for example, you might want to shut off some of those buffer processors, those cluster controllers. Right? When did ICL get around to cluster controllers? Early 70s, 7502, 7503, by the way. And the way the agent sets were connected to buffer processors, if you did that, you didn't take down a whole logical group of terminals. You didn't knock out France or Benelux or something for the duration, because they were wired such that you effectively degrade a number of groups rather than destroy the operation of one group. So SICOM would allow you to do that. Alternatively, I'll talk a bit later about the network handling, but you might want to stop all the inputs from the network. Now there's a catch there, because the CETA network at the time, incidentally, was electronic, but it was not computer-based. Yes, there were switching centres, but literally they just switched circuits, really. No store and forward. So if you missed a message, remember that was business, revenue, then you weren't going to get it back unless you requested it from the sending airline, and of course you wouldn't know that they sent one in the first place. So how could you ask? So something had to be done about making sure that messages were never lost, even if their processing was delayed a bit in emergencies, and we'll see in a moment how it was done. Right, I think that's enough about designing for failure, actually. Design for performance. Well, we know what a transaction is now. It's essentially a message pair, in, out. The 2 seconds target, by the way, in those days was deemed to be about as fast as it usefully should be for a real-time system, because it was felt, I don't know if this is still the theory, that if you went faster than that, you would kind of hex the user and, you know, harass him or her. Now, how do we achieve that sort of level of performance and the throughput required, which, as I say, in morning peaks could be, well, a few thousand a second, an hour. The key to it, as I've hinted, was file accessing. And so contorts in particular, but also constituent application programs, all played a part in that. First of all, the entire online system, including contorts and all the applications processing and so on, was core resident. No overlays. Contorts actually occupy about 12,000 words, quite a modest operating system by today's standards. And normally, there would also be an area of about 6,000 words for concurrent background jobs, like those schedule changes, those nightly updates, those file copy recoveries, if necessary, whatever, dumps. When pressure built up, transaction pressure built up, then that re-entrant programming would come into play, and you would start processing concurrently a number of transactions. And the objective there was not to get the actual processing done faster, because that was no big deal anyway. It was actually to ensure that when the system was busy, there was a constant queue of drum access requests waiting to go, with no waiting in between. As soon as one had finished, boom, off goes the other one. Normally, you'd also exploit the fact that you've got duplicated copies of the files, so you could read from either copy. Separate controllers, everything. Right? Of course, you'd have to write to both, but then a lot more reads than writes. The schedule scan, as we called it, the prioritization of tasks within the operating system contorts, was arranged such that the highest priority for processing interrupts and getting on with something else were actually the drum subsystems. Not the communications, the drum subsystems. So they would always get priority. Other features were that in processing interrupts, for those of you familiar with that, you needed something called interrupt lockout, so you didn't get interrupted while you're doing something essential. We were only allowed, under interrupt lockout, for immediate servicing of any interrupt, about 3 or 4 instruction executions. Again, a discipline which I look for in vain in subsequent years in standard operating systems. And the reason for having concurrent processing then was so that whenever something finished on one of the drum subsystems, there was something else waiting to go immediately, and it took priority. On top of that, on the fast trans, where you've got those moving heads, the passenger name indices linking flight records to passenger records, were all placed tightly together because you access them a lot. Therefore, when you access an index, there is almost no head movement involved on the device. And so, you did better than that nominal average access time. On top of that, even, the fast-RAN handler, part of Contours, would actually look down its queue of outstanding requests and pick the one whose address was nearest to where the heads were from the last one. So it wasn't a case of first in, first out in the queue. Nowadays, of course, when you don't make your own file handling systems or database management, you don't get to decide like that where you're going to put your files. We had to. Another device, actually, to speed things up and reduce accesses, familiar these days, whenever you make a booking of any kind on it with anybody, they give you a reference number, don't they? Which you may or may not retain and remember. And we did that. It was effectively a coded fast-RAN address for that passenger record, so that one access would get it. You didn't need to go through indices. On the other hand, if they didn't have the reference number, then there are all kinds of ways we could get to the record. I'll touch on those later. Now, this little formula represented the kind of philosophy of Contours and the beacon system, really. And it basically said there are relationships between these factors. The throughput, how much can you handle in a given time, the level of concurrent processing, and the existence time. In other words, how long is a transaction in the system. Now, interestingly, we found there was an optimum value for C. It was not just incremental. Increasing C, the level of concurrency, did not mean that you got more and more throughput. It tailed off. And the reasons for that were basically that, of course, every transaction has its own context. Right? Every time you change from processing a bit further on one to move to another, you've got to unload all the registers, load them up again, etc., etc. So there are diminishing returns from concurrency. This was something I found in the early 70s when I was privileged to attend a transaction processing course in ICL that had not apparently occurred to them. And in fact, unlike us, we on Beacon, they got themselves into terrible knots with all kinds of multi-server queuing theory and stuff. We didn't do that. And in fact, they managed to prove, with the aid of queuing theory, that you could exceed the physical speed of the disk drives, which suggested maybe there was a flaw in the calculation somewhere. So that simple little formula underlay the whole design of Beacon. Now I'd like to turn to that subject I pointed out at the start, instrumentation. We counted or timed on Beacon everything that moved. For example, how did we know that our average fast-RAN access time was not 92 milliseconds, but more like 65? Because we timed them all. We timed everything, or we counted everything. Messages coming in from that CETA network, we knew what their average length was. Why would we care? Well, for one thing, we could tune the size of the buffers involved in receiving data off the lines, and for that matter, writing them away after rough editing onto the drum for subsequent processing. So all these things mattered a great deal, and precious as the memory was, we had loads and loads of counters and timers in there. So we did know what the existence time of the transaction were in the system, because you'd start a timer at the beginning and you see what it was at the end and write it away. Now this too was something which, around about 1973, I was actually sent on a typical short-lived assignment in ICL actually to see what sort of instrumentation they got on George III and then figure out what it should be. Well, the first part was fairly easy, there wasn't any. Before I could get round to the second part of the task, switched on to something else. But Contorts was, again, in this case, perhaps somewhat ahead of its time. Now, message handling. There were 16 lines coming in from that Nunn Store and Forward London Switching Centre of CETA, and 4 going out. And they were all simplex lines, 75 bits per second, using 5-hole CCITT alphabet number 2. Now, first thing was, we can't afford to lose them. So, on the end of each incoming line was one of these devices from Siemens, the T-Lock 15, which would punch tape from the incoming data, and normally, on receipt of a signal from the central computer, it would immediately read the data on and again to the computer. But if for some reason it didn't get a signal from the computer, then it wouldn't read on until the signal came. Instead, a tape loop would build up. And when we were having lots of trouble after the phase 2 cutover with morning peak times, a very useful feature, in fact, was simply to use a system command which said, shut off all the message input. And tapes would build up in these cassettes, and such was the rate of input, even at 75 bits a second, you didn't have to be to shut them off for very long before these cassettes filled up and overflowed. And in fact, within about an hour and a half, you could safely say that a large part of the ground communications room was about waist high in paper tape, which was a pain because it then had to be carefully bailed up when you were ready to read it back in. And there was a period of unhappy relationship with the BA ground communications staff, which you'll probably remember. Now, having read in the messages and done a rough check on them and buffered them, we come to the next problem. We've got to carefully edit and decompose the message content. Remember, that was in AirImp format. But because in that pre-reservation system era, all these messages are cut by hand on Teleprinter somewhere, the AirImp format tends to get sort of somewhat overlooked and bowdlerized as often as not, in fact more often than not. And early systems like Panamac and Sabre, who came to address this problem, found that they were rejecting about 70%, being not compatible with the AirImp format. And Beacon contented itself with rejecting 7%. And for a very competitive line of business, actually, these early systems were very open to each other. You know, people would visit rival systems sites and they'd have the tour and the presentation and the demo and this and that. And habitually, when they got to the ground communications room, they'd say, and what's your rejection rate? And the manager there would proudly say, 7%. You mean 70? No, 7. This is the best system in the world. Now, how was that done? The answer was something called G-edit, General Edit. It was an interpretive language for editing. And you could refine the, if you will, the source, the language as much as you care to, as much as you could afford to burn processor time on it. So there's a trade-off there. That's why I say, in the case of Beacon, we settled for 7%. So what would happen was that the message would get parsed and, in most cases, corrected by this G-edit program. After which, the contents of the message would be sort of ready for normal transaction type processing by the same sort of routines, and that transformation was effected by a program called Grunt, for reasons I never dared ask. Another particular feature I'll mention is name searches. As I said, ideally, somebody would ring up, they want to change their booking or whatever it is, they give you the reference number, the coded address of their record on the drum, and bang, you've got it. Otherwise, they might say, no, I don't know what that is, you know, my name's Knight. And I'm foreign, perhaps. So, how do you spell Knight? A number of possibilities occur to me. Well, we actually had a facility which would look at the name as presented. It might have come on a message for that matter. Look at the name and get the best, I've forgotten the word, the best sounding fits from the list of passengers for the flight in question. Failing that, you could, of course, get a printout on your agent's set Teleprinter of the whole flight list, passenger list. But even with the aircraft of those days, you've got perhaps 100 names at Teleprinter speed. That's a pretty tedious last resort. Finally, I should mention space control. Not what you might think. It's basically about control of seat space. And a very important feature of the system was that space controllers could apply profiles based on experience, whether statistical or bottom of seat of pants, about booking levels during the life of the 11-month life of the flight in the system. And sometimes you'd want to overbook because you'd know you're going to get a bunch of no-shows on that route towards the end of the life of the flight from previous experience. So other times you might want to underbook because you're hoping to get more expensive seats sold or longer segment perhaps. So we had great control over space control online again as a result of that. Finally, I said I'd give a postscript. After the reservations application, a whole succession of applications were added. First up was PALC, Passenger Acceptance and Load Control, and that did use small screen visual display units incidentally. Then there was CALC, Cargo Acceptance and Load Control. Then there was Flight Information and Control of Operations. and various marketing applications, and weight and balance, and so on. Meanwhile, of course, BOAC was doing the same thing with Boadicea on an IBM basis. In the early 1970s, the government decreed that its two airlines, BEA and BOAC, should become one. The British Airways we're familiar with. And that inevitably led to a debate about, well, how are we going to rationalise the IT? And according to people who were there, as I was not, committees were formed and studies done and so forth. And this is a Univac person talking, by the way, to me. Beacon won all the arguments about cost per transaction and so forth. And the boss of Boadicea, Peter Herman, whose name escapes me for the moment, won all the political arguments, and thereafter gradually Beacon withered on the vine. Meanwhile, of course, around the world there was a battle royal going on between Univac and IBM for airline systems. One of the few areas where the long dominance of IBM mainframes was seriously challenged. It probably, depending how you measure it, always just about had the edge in terms of sales achievement over Univac, but it was a close-run thing. To a degree, in some places like China, it goes on to this day, I gather. In 1987, 4 airlines, which happened to be Univac users, decided to band together and form something called Amadeus. This was not a new idea, but this time it got off the ground. It was basically to do reservations and indeed other applications for airlines on a kind of online bureau basis, instead of having separate in-house systems. In America, American Airlines was doing a similar thing based on that Sabre system, which I believe it continues to this day. And indeed, it's Sabre which is the profitable part of American Airlines these days, not the airline. Amadeus, nowadays, I believe it's just moving over to new kit and Linux even, basis. But it's got centres in Munich, in Sydney, in Miami. Supposedly has hundreds of thousands of online terminals. I don't suppose they're dedicated to Amadeus work. 2,000 technicians, and God knows how many transactions an hour and so forth. So that's typical. There are about 150 airlines, right, from familiar names like Qantas and indeed British Airways using it, down to things like Air Congo and Air Montenegro. So that seems to be the trend of this type of system at the moment. But of course, in the meantime, transaction processing and call centres, for that matter, have become part of our everyday existence. And despite having missed some things out, as I knew I would, that's the end, gentlemen and ladies.
Thank you, Michael.
Okay.
I think I would sum up your project as being one of those few heroic projects, in that you set out to do something which had not been done before. You didn't know you couldn't do it, so you did it. All the subsequent projects, of course, were failures.
It helped not to have too many family or other domestic distractions, incidentally. Wouldn't do it now.
I invite questions from Michael.
Two questions. Where was all this physically?
Oh, thank you, yes.
And was there a person called Huck working on the project?
Who?
A person called Huck working on the project you know.
Huckle, Dave Huckle.
Dave, okay, that's who it was.
Yes, I should have told you where it was. Just down the Cromwell Road.
Okay, you look impressive.
Is it still a Sainsbury's these days? There was a new,
Where
lovely new building, West London Air Terminal. And the computer system resided in about 6,000 square feet of air-conditioned space on the 3rd floor. And that main reservation hall, I showed you a view of the beginning, resided on the 4th floor. And as I say, later on, then there was another couple of hundred terminals in clusters out, remotely connected. The project started late, actually. One of our subsequent rules of projects, sizable projects, is that they always start late, as you'll know if you follow current affairs at all, because the decision isn't sufficiently critical until you've reached a point where the chances of a timely and successful completion are seriously diminished. And the second rule is that the project will run into all kinds of entirely unexpected obstacles. And indeed, about 2 months after the contract was awarded, early in '64, there was a major fire at that West London Air Terminal as it was nearing completion, which had its effects, amongst other places, on 3rd and 4th floors, and so that put a spoke in the wheel as well. But that first phase, as I said earlier, did actually get it done on time.
Using modern parts, the original drivers for this, was it because BEA saw this as a competitive edge, or was it because they just couldn't cope manually with the previous system?
Thank you for that too, because that's another bit I missed out. Not wishing to slavishly follow the notes. The original motive for these systems, not to be lightly undertaken back in those days, as everybody knew, was cost reduction. And indeed, perhaps the reason why they started in America was that the reservation function, passenger service function generally in the airlines, tended to be the least strongly unionized. So when cold winds blew financially, some things never change, of course, for the airline industry, you're looking to cut costs, you want to reduce your wage bill, where better than in the reservations function. That was certainly the original motive at Eastern. Now, on top of that, of course, you get less quantifiable factors like improved load factors from that space control and so on, and improved marketing and so forth. Then, yes, there's the image, the competitive edge, you know, the boastful adverts and so on. And those are probably the 3 key reasons. As the habit grew, smaller and smaller airlines actually, you know, stuck their neck out and took reservation systems, and more the unquantifiable reasons like improved load factors. Well, how do you prove that? So many different external factors are going to affect that. You know, they became prominent. It wasn't about cost reduction. There wasn't that much cost to reduce. Incidentally, BOEC, talking of such cases, only carried about 1/5 the number of passengers that BEA did. So where BEA was actually 5th largest carrier in those days, BOEC was 35th. On the other hand, of course, being the intercontinental carrier, it had, average fare was more than 10 times what it was for BEA, which gave plenty of scope for profligacy, of course, which in due time was exercised. I believe the Boadicea reservations phase, according to their ads anyway, their recruitment ads at the time, took about 400 man-years rather than the 80 at Beacon.
On the basis that no IT project ever did save money, did it with Beacon?
Oh, I think so, for the bigger airlines. And you could quantify it very readily, of course, if what you're doing is saying we need, despite growth in passenger numbers, we need many fewer staff to handle it. When you think about it, suppose you've got a booking, you want to change it. Well, when you took the booking, before the computer system appeared, details would be written on a card. That would go zipping up to the end of the room on a conveyor, and it would get manually filed, that written card. It wouldn't get punched. Now, damn it, somebody wants to change their booking, or other arrangements, or cancel for that matter. Now you've got to get it back. The guy's on the phone. Yeah. So you can see how that sort of productivity gain, was readily quantifiable actually. Not terribly popular amongst staff at BEA anymore than anywhere else, but there we go.
More questions?
Can I ask you another question, just to say perhaps just a word more? I was intrigued by this, I think you called it G-edit. Essentially, as I understood it, you had a sort of effectively a paper tape buffer in that when you couldn't process the incoming messages, you got more and more paper tape punched with the transactions on.
That's right.
You said you had a piece of software that was used to correct essentially the syntactic errors in the message. That presumably was an interactive process with an operator.
No.
I just wondered how it worked.
No, it was very much stored program. As I say, an interpretive language was devised for editing. Whether it was really general edit is a moot point, but anyway, hence the name G-edit. Once the message had been read in, forget about the paper tape now, it's in the system, it's buffered on drum, and then on a queue basis, this G-edit interpreter would pull the message down and parse it and say there should be a space there, or there shouldn't be a comma there, etc., etc. Long par should be one word, not long par, etc., etc. And instead of bouncing it, it would say, right, put it together, So it would look at the context. And how much context you care to take into account really depended, as I say, how much processor time you wanted to burn. As I say, Beacon settled for 7% rejection rate.
Did you ever get it wrong in terms of its interpretation?
How would we ever know?
Anybody who got the wrong seat should complain now.
I don't think so. If it let through something which was in error, which then went on into being processed like a transaction, if the anomaly would be spotted at that point anyway. What happened with rejected messages, of course, was that they were then looked at by hand by ground communications staff, and they would then re-input correctly. So again, from the point of view of cost reduction and general efficiency, 7% out of thousands of messages a day, is a damn sight better than handling 70% rejections.
Yes.
But just ask Mike to comment on another legacy of the Beacon system, which is that there's an indirect connection with the later system, namely that EMIDEC was one of the Univac designers who But he went on, when ICL went through one of his reorganisations that brought in a new wave of management, the Jeffrey Crossy.
Like airline people instead.
This is the Jeffrey Crossy era. EMIDEC was appointed product development director. So he had considerable power and autonomy, and he was obviously an enthusiast for TP systems, because he went on to impose on the 2900 range, which had at that time in October 72, I think it was, the EMIDEC came in. By that time, the 2900 range had been designed, spec of operating systems settled, and BMEB was being implemented. And Mark came along and said, I really want a TP system, and you're not doing one like it, so you've got to do it.
Yeah.
So we set a project up for something that was called BMEK. That absorbed a lot of attention and resource and effort. but then they didn't meet the claims that were made, and didn't.
Wilmot finally killed it.
Yeah,
Yes.
that's right. No, it absorbed an awful lot of effort. Anyway, you may comment on that bit of history.
Well, I wasn't going to mention names because inevitably one would fail to do justice to those who did mention, but the architect of this system was in fact Ed Mack, and he had been involved also previously at Eastern Airlines. And I have asked the question actually of one or two people who were involved with VMEK to a greater or lesser extent, as I mercifully was not, despite being in ICR, what went wrong, because it was supposed to be contorts of 2900. It wasn't instead of VMEB, but it was for serious TP cases, yeah? And it was going to be feature lean, not feature rich, for example. And I said, well, what went wrong? And such answers as I've elicited, you know, still don't really tell me. I have one view, which is that Ed was at his very best driving a project of about 30 people. He was at much less than his best when he subsequently found himself directing a product development group of around 3,000. And I think that was part of the problem because, you know, he couldn't give VMEK perhaps the attention it needed. The other thing was mission creep, because what the developers would tell you is that marketing kept moving the functional goalposts. But it certainly scarred marketing. In fact, at one time, totally different story, I was trying in the late 70s to get a sub-mainframe unified range of products to replace the rag bag we had at the time, which was called a high volume products range. And Ed Mack was against it because he was against distributed processing. You know, famously, distributed incompetence, he said. And eventually, Decision Point came, and Peter Ellis was the group marketing director, and he was in favour of this new range. And Ed Mack finally said, Peter, am I right in thinking that this new range, this H3P you're talking about, would be unlike anything we've got now? Yes, said Peter. And so it would need a new operating system? Yes, I suppose so, said Peter Ellis. And Ed Mack said, Peter, do you really want me to start another VMEK? And that was the end of the high volume product range. So I don't know what went wrong there, really.
Any more? Yes, one more. Two.
Michael touched on the subject of the programming teams, mixed staff from BEA and Univac. I might add a little bit on that, which was of interest. I was on the BEA side of this. We decided that for the sake of continuity after Univac departed, each team should be a mixed team of BEA and Univac people. And as he said, the leader was the best person available out of that mixed team, not necessarily from Univac, not necessarily BEA. And that we managed to keep going, I think, throughout. The problem of having staff mixed from the two organisations was that the Univac staff generally were paid considerably more, so we believe, than the BEA staff. On the other hand, the BEA staff had travel concessions and more holidays per year. So this balanced fairly well, and I think that did a lot to keep it smooth. We also had a no poaching agreement between the two organisations.
I didn't know that.
And this worked very well until, on one occasion, Univac stole one of our senior programmers. Within a couple of weeks, we had taken over their chief engineer.
Seems fair, actually. Yeah, well, eventually, I couldn't detail the timing, but quite a few leading lights on the BEA side of the project team did join Univac, and indeed ICL in due course.
Yet again, the programmers come from all directions,
Yeah.
as well as from history careers. Yes.
Can I ask a question about the drum? I've not used the drum. Now, Consorts was the entire operating system, so the software interface went right up to the hardware of the drum, I suppose.
Yeah.
At some point you were saying how, I inferred from what you said, that the throughput on the drum minimised latency if you kept the transactions going straight at it.
Yeah.
Was that managed by software or by the hardware of the drum itself?
Software.
By software.
Yeah.
Right.
There's another feature about the drums, incidentally. They have something called an interlace. Again, this is counterintuitive. But we weren't talking about translating big chunks of data, quite small records in each case. And if you just let it transfer at its normal rate, then it would come across very fast down the drum subsystem channel. And every word it transferred took 2 memory cycles to do it. Stole them from the program running. And that bothered us because it meant we couldn't guarantee to get quickly enough to interrupts, particularly drum channel interrupts. Several channels of the drums, let's face it. And so we thought, this fast transfer rate, as opposed to access time, is a liability. So we use this interlace facility to slug the transfer rate by to about 25% of what it could be. Which again, as I say, is counterintuitive in a way, but the purpose was, not to have your processor suddenly brought to a halt practically by the actual transfer of data.
Okay. Oh, Dan.
Just a question from behind the camera. You mentioned you were looking at performance figures, performance targets for the system. Who provided those? Was that what Univac said, oh, we could do this for you? Or did the customer say, this is what we want? Was it sales driven or was it need driven?
Well, I have assumed over the decades that they were effectively defined by Univac. However, there are people amongst us today who probably know better. John, what's your recollection?
I can't honestly remember that. I think it was probably a joint agreement that this would be satisfactory to us and achievable by you.
Yeah.
But I don't recall quite how that was designed.
Unlike IBM, where they promised it and pulled bloody infantry out to try and deliver it to the customer.
Well, I don't know. Again, I have to rely.
I have experience.
The Bodicea story, I have to rely on hearsay. I mean, I found myself beginning of 1968 briefly alongside, in a company that shall be nameless, alongside some Bodicea veterans, and up to that point, it had never occurred to me that Bodicea wasn't a 24/7 type system. But in fact, it only set out, all being well, to run online 14 hours a day. And all the things which Beacon did concurrently with the online system, were actually done in the other 10 hours of the day on that system, notwithstanding the fact that it ended up with 3 IBM 360/65s, I remember, whereas the bid, I think, featured 2 50s.
Standard IBM server.
It's called OS 360 in the middle.
So that's odd because you'd think that the VOAC system would be the one that would need to keep going in daytime all around the world.
It would. One of their 3 computers was in New York, so that probably helped. The other distinguishing thing about Bodicea compared with Beacon is that by then I suppose it was 1965 that the Boadicea contract was placed. Well, two things. One, they used VDUs for terminals, not agent sets anymore. The other thing was, I think part of the success of the sale was that IBM offered a package, an application package. People were starting to realise in those days, you know, why should everybody write their own payroll, accounting, etc., etc.? It ought to be possible to have a package and parameterise it. So IBM offered this airline reservations package. It's called PARS. I suspect it came from American Airlines. On closer examination, it turned out it was ideal for a domestic US airline and not at all suitable for an international carrier. And so IPARS emerged 400 man years later, international PARS, and then BOAC became a big player for a while in the software industry because they were running around the world peddling copies of IPARS to recoup some of the costs, presumably.
Very quick, I cannot resist having just booked a seat on Eurostar, which uses Sabre software.
Oh, does it?
Yes, you will discover that if you're, well, most people who travel by train, there are two preferences. One is window or aisle, and the other one is facing the engine or back to engine. You can do window and aisle, but on an aircraft you don't get a choice. Oh, back to engine, and that's why on Eurostar you can't have that choice.
Interesting insight.
When I go to Eurostar, they always seem to put it back to engine anyway. So. In not summing up, but thanking Michael, I have to admit to being really rather humbled by the talk because of the following. I gave a talk to this society back in September about the Iron Apples 2 project, the ICL in Cambridge. And we were boasted, I know I made the boast then about that talk, that we produced the first time-sharing system in the UK. I'm very proud of that. The dates of that project were more or less the same dates as yours. And I think yours was the greater achievement. So thank you very much for inviting us. Thank you. Can I just make some announcements about future meetings?